So I have to show in this invariant in green that I is between 0 and A. Okay? I can do this on paper once or twice, that's quite boring. So I know that since the 70s, almost 50 years ago, people have designed interval analysis that will essentially compute that. Now let's try to go through the same approach for slightly more complex properties and see what happens. So before I move to hyperproperties, let's cover the case of all trace properties. So again, there is a very nice theorem that does it for us. Let's assume we take any semantic property that is a set of traces. It's not necessarily safety, it's not necessarily liveness. So essentially the two theorems I just mentioned do not apply. We don't know if we have a proof method quite yet. But there is this very nice theorem by Alpern and Schneider that tells you that if you take any semantic property, you can actually decompose it into the intersection of two sets of executions, so of the conjunction of two properties, one of which is a safety property, the other of which is a liveness property, and we have already seen we have proof methods for liveness and for safety. So we can just consider this problem is solved. Okay? Now, what if we move to hyperproperties? We just go to things that are not properties. So let's look first at the security example which I mentioned a bit earlier, which was non-interference. So for non-interference, as I said, what we want to prove is that if you run a program twice with states that differ only in the initial value of a sacred variable, the output should not differ for any of the observable variables. So how can I do that? Actually, there is a technique that has been covered in a number of works. Any hyperproperty for which counterexample can always be made with fewer than k executions. Okay? So if you take non-interference, this is called two safety because the counterexample for non-interference is just, if I go back to the definition I gave for it right here, is just a pair of executions for which you run P with one value of V0, one value of V1, and you get different observations. Okay? So that means that information flow is two safety, and we could also have other hyperproperties which are essentially not like this one, but need to be refuted with three executions, that is free safety, and so on. And actually, we can generalize the self-composition proof method that I just mentioned for non-interference here. So this was for a two safety property. I run P twice, and I can reduce my initial hyperproperty to some safety property. Well, if you have any k-safety hyperproperty, you can reduce it to safety by composing the program with itself k times. And of course, the higher the k, the higher the price to pay for that, because it's just much bigger a program, k times the number of variables, k times the number of statements, proofs are usually a little more than linear in the size of the program, so that makes it more costly on paper and also to automate. Okay, so now let's look at the general case of hyperproperties. So there is actually a very beautiful theorem too, which is, I forgot, I think it's Alpern and, so it's Clarkson and Alpern, so one of the two authors of the initial safety liveness work, and some other author proved that we can also decompose hyperproperties in a very similar way, except that some bad news will come a little bit further down the road. Okay, so but first let's look at the nice thing. If I give you any hyperproperty H, then you can decompose it into two hyperproperties that are respectively what is called hypersafety and hyperliveness. And what are hypersafety and hyperliveness? So hypersafety is essentially any hyperproperty that can always be refuted with a finite counterexample. So finite counterexample means finitely many finite executions. So that's very nice, but the first piece of bad news comes here. Hypersafety is not case safety for any case. So the self-composition technique I just mentioned will not work because it could be that you can decompose property this way with unbounded sizes of counterexamples. You have no fixed scale such that any counterexample is of size at most k executions. So that means that the self-composition technique will not work here. Then there is the hyperliveness part, which is essentially a little bit more complex to see. So essentially what hyperliveness means is cannot be refuted with any finite observation. Finite observation is essentially a finite number of finite traces. So there are now two ways of becoming infinite. One way is to have infinitely many executions, and another way is to have, infinitely many executions, which would actually be finite, or not. And the other way is to have infinite executions in the first place. So essentially, if you remember what liveness was about, it was just about infinite executions, but now we have also to deal with possibly unbounded number of executions to look at. And actually, the smoothness case is a case where what it means for a function not to be continuous, it means you have infinitely many executions that have some bad behavior that break your target property. So it means that essentially what we have here is something that is very, very far from the liveness thing where breaking functions will work. Here it will just not work. Okay? So there is a piece of recent good news, which is actually not necessarily so good. So Kuzo and Wong have proposed this year at Ecole something that is called hyperlogics. That gives you a set of rules to reason over hyperproperty. That's very beautiful. However, there is one big limitation which is inherent in this system, which comes from the hyperproperty framework, is that in this system you cannot do approximation. So it's really very poor if you want to later automate this into a proof, some automatic proving tool. It's very nice to have, but hyperproperties are just too hard for it. So now what we are going to do is to look a little bit into several methods that you can actually automate. You can find static analyses that implement them, and that will reason over hyperproperties. So I have planned to talk about three. Maybe I don't remember what is the time. Okay, so maybe we have time to talk about the three. We'll see. So actually, the first two have some inspiration from the safety. So essentially for the first two, we are going to reduce to some kind of safety property. And actually there are a lot of static analyses that do that. I just mentioned the self-composition method. So one of the two will actually leverage self-composition. The other one will be doing something different. And for the last part, I will talk about some relational analysis for hyperliveness, that is for smoothness properties, that is really doing something very different. So essentially this is not an exhaustive list of the possible static analyses you can find to reason about hyperproperties. It's just a list to show a little bit of the diversity here and to show that there are a lot of things we do not know how to do. Okay, so I will first start with something that is quite simple conceptually, but pretty interesting if you try to understand how it works and what makes it work, like how to prove it. So essentially what data analysis does is essentially some kind of analysis that searches for information flows in a way where you are actually just going to track how some so-called taints propagate through your program. So let's first assume that we are going to be able to tag each variable with a taint, which could be also seen as a security level. So simplest view is you have just two taints. You may have a lattice with more than two taints. So let's assume you have, for instance, black, which is smaller than blue, which is smaller than red. So black could mean this is sorry, I got the other wrong, I meant the other way. Sorry. Black should be greater than blue, should be greater than red. Red should be separate here. So let's assume that I run my program here with initial value for x tainted in red, everything else is tainted in black. If I propagate the taint, when I do t equal to f of x, essentially t will get the taint because we use directly x to compute it, and x is tainted in red, so we take the greatest color that is tainted in the arguments of the function. And we keep going, so essentially here we cannot quite see the color, but essentially here I think y was blue, and u also becomes blue, and at the very end we just compute v equal a to h applied to the three variables c, u, z, and the taint that wins it is the right one, because it is the greatest element in the lattice. So we see we have a taint, we have a pass, well at least we have a possible pass of information from x to t and then to v. But what we also learn here is that we don't have a pass from x to u, because when we compute u, we just use we just use y, which is not tainted in red. So we learn another approximation of the information flows we have here. And that's essentially something that you can automate, and you can do static analysis over more complex programs, like here is a code with a loop. So what is interesting here is that, again, we are going to assume that only x is tainted in the beginning. We are going to iterate this sequence of assignments, so the last one is just incrementing y for the sake of counting. And here we have those statements where we just copy one variable to another. So if we iterate the loop a little bit, the first iterate will keep z black because y was initially black. Y now becomes red, so actually at the next iteration, z is going to become red too. If you just unfold the loop, you have a sequence of a cascade of flow propagation. So essentially what I've sketched here is what many security analyses have been doing for a very long time. This is at the core of many security reasoning tools. And now what is interesting is how to prove this correct. So there are several ways. I will mention two. So the first is, I would say, the simplest way, which is to just say we are going to change a little bit what the semantics of programs is. And this will make our semantic proof much simpler. So we are just going to say that now, instead of having variables that just store values, we are just going to say that a value is a value plus a taint. So I just changed the semantics of my program with the addition of the taint. Whenever I have a value, it's not just one, it's one red, which is different from one black. Then memory states just consist of variables that store such tainted values, and states have tainted memories. And I just extend the transition system accordingly. And what I get here is essentially some safety property. So that's quite magical. Essentially, I keep my program, I change the semantics, and essentially if I want to prove that there is no information flow from one variable to another, what I'm going to do is to prove some stronger safety property than the information flow property I wanted to reason over. It's not the same, it's not semantically equivalent. It is stronger, that is, there are programs for which there is no information flow, no security bug, but the taint semantics itself, in the complete, will always tell you your program is rejected. So I make a very big approximation step before even I start doing an abstraction or even thinking about the analysis. So that's very coarse analysis kind, but this is a proof method that's quite beautiful because it shows that in this approach, what we do is we can really view the abstraction that we do as just a semantic modification step. So then static analysis is very simple. As you could see, propagating taints is really no complex abstract domain. The second proof, so I forgot to acknowledge authors here. I think it's very beautiful work by Munir, Asaf, and co-authors about, I think, paper 17, is to change the semantics again, but this time, instead of just adding tails everywhere, you just make the semantics itself something that computes sets of behaviors. And I mean the concrete semantics. So that's also a very nice proof method. So the first one is very nice because of simplicity. This one, I would say, is much more elegant because you can see several steps. And in the end, what the proof of the analysis is about is really about hyperproperties. That is, if we want to track information flows, we expect to talk about some hyperproperty, and what we are going to do here is have this hypercollecting semantics that compute sets of behaviors of your program. The semantics of P should be an element of this hypercollecting semantics. You prove this once on paper, and then you can prove taint as an abstraction of this hypercollecting semantics, which is nice standard abstract interpretation again. So that's two ways to prove this that are quite nice. Now, why are we not going to stop here? It's because, like I said, this property itself is much stronger than what we typically want to prove. So, typically we want to prove that we have no information flow from X to Y. For many programs, as soon as you say we are going to do data analysis or some similar kind of dependence analysis, we know we are not going to make it. So I'm going to show it immediately. So, and for this, I will just show what happens if you have programs with some conditions. Okay, so if you do data analysis with conditions, really the first example is the case of an explicit flow. So this is a program I gave in the beginning of my talk. I gave a variation of that. So you have secret X, then you test on X. Depending on the value of the test, you are going to compute to store one value or another into Y, and there is an information flow here, which is not direct. It is, sorry, this is, I am sorry, I made a typo here. This is implicit flow. So implicit flow means that you have a flow that goes through the condition. So if I do taint analysis here, as we expect, it's going to say that there is a taint from X to Y. The first step is this test is tainted. So what this means is that whatever assignment we do under the test also becomes tainted. So there is a taint that gets into Y, and this is implicit flow that is created. Sorry for the time. Now the second is imprecise implicit flow. So in this case, what we have here is this compiled program I gave also in the very beginning, where most branches actually store the same value into Y. Okay, so if I just apply the same analysis, the same thing will happen. That is, we are going to have a tainted test here, and this will cause both branches assignments to become tainted, which is very big in precision, because in this case, as you can see, whatever the value of X, you know that Y will store 1 in the end, so there is no information flow. And this loss in precision is inherent in the taint abstraction. So, in order to do better, we are going to look at a second family of static analysis for 2 safety, which is much more precise and uses very different kinds of abstract interpretation techniques. So one thing is, if you have any questions, feel free to stop me at any time in the talk. So now is probably a good time. No question? I will just continue then. So the second one is to actually just go back to this self-composition intuition. I just mentioned self-composition as a systematic proof method for 2 safety. So let's see what self-composition means, how it works, and how we can turn it into static analysis. I will just give the main intuition for this here. Actually, implementing static analysis and do that is fairly tricky. So, and I don't want to get into the details, I just want to give the high-level principles. So, first, if we remember what the self-composition proof method looked like on paper, essentially what it says is you run P and P prime, so you run twice your same program, once with the standard variables, one with the copy of the prime copy of the variable. So essentially you run P in red, and then you run P prime in green. So what the equal means actually here is, first when you are running P, the prime state does not change, so these are all equal. You are running P, you are making a number of steps in P, then you finish running P, then you are not going to modify anymore the state of P, you just run P prime, and you can combine these 2 executions into one. Okay? Now the question is how to make it a little bit more efficient for systematic reasoning? Well, the intuition is very similar. It's very simple. Whenever we do a step here like this one, and we are going to do a similar step when we run P prime, well, we could actually make this step just one in the semantic point of view. That is, we are going to group this step and that step into a first step where you are actually just modifying both the non-prime and the prime variables. And if we can prove that we have some invariant of this program where we combine into one execution of P and P prime, the executions of P and the execution of P prime, then we are actually going to win. So now how to actually make these strong relations in each state? Well, of course, we are not going to get to this with cheap abstraction like interval abstraction. What we need is to really establish equality. Like here you have equivalent symbols for each of these states. We have to maintain a very tight relation between the prime and non-prime variables. So we are going to turn to more expressive, more costly abstract domains like convex polyhedra or linear equality. How does it work? Well, let's see an example. So I give you actually a value. So this is a different program. First, we are going to look at straight line code and see what happens. So you have here a program that starts with secret x, and we make a series of assignments. Actually, we are going to first add x to y, store the result in t, we add x to c, we store the result in u, then we compute the difference between t and u, store this in v. So as you can see, whatever x is, because when you add x to both t and u, is going to cancel each other. So this last line is going to not depend on the x. So essentially, we expect to prove that v does not depend on x. Okay, so how to do that? We are just going to run to do some abstract interpretation of the program, except that we are going to do it in a slightly non-standard way. Whenever we see one variable, we are going to have two versions of it, the non-prime and the prime version. So, and we are going to make the step with both a prime assignment and a non-prime assignment. Okay, so let's first analyze t equal to y plus x. So we start from a state where you have all equalities between prime and non-prime except for the secret x. Okay, we are just running the program twice. So this is essentially just a result of the assertion that y is equal to y prime and so on. Each step is going to be analyzed in some abstract domain, like for instance linear equalities. In this case, the car abstract domain of linear equalities would work. So you see the first assignment will just enrich the state with the equality t equal to y plus t plus x, t prime equal to y plus x prime. So actually this should be y prime, but this is not a typo. Actually this is y because I know that y is equal to y prime. So actually I have here just contracted steps a little bit. Inside the abstract domain, this kind of reasoning happens automatically without doing anything. You are going to have some normalization that will happen, and you will see on the one. We do the same for the next one. So we get this time u equal to z plus x, u prime equal to z plus x prime. So again, this should be z prime, but same thing, z is equal to z prime, so we get z here. And as we expect, at the very end, what happens is we just get, where is it? So there are too many things. Yes, v equal to v prime equal to y minus z. Okay? So that happens, that works pretty well here because we have straight line code. We don't have condition test. If we have condition test, everything becomes much harder because what could happen is the first execution on prime. So actually, let's go back to an example. If we just try to look, so this was the last example of the data analysis that did not work so well because of the condition test. If I just try with the same method as I described it, it's not quite going to work because I have one execution that will go through maybe the first branch, the other goes through the second branch, and I don't have a good way to address this in this method. So what to do? Well, actually, there are ways to deal with that, which are more complex, so that's why I will not give all the details. There are actually many solutions that we can do to keep doing this abstract interpretation, where we run two executions in one single analysis, which is actually quite challenging. So one example is to actually consider that whenever paths diverge, you halve the state. So that is, you just say the prime and non-prime live their life, and you lose many relations. So essentially, this is easy to implement, but this assumes essentially the worst possible information flow, and essentially we are back to the same issue as we had in the taint analysis. So that's not very good. What is a little bit better is to just call for a different abstract domain to the rescue, which is essentially based on something that is very popular in security, like my colleague CNRS told me, which is essentially to do some symbolic execution and to turn it into an abstract domain, which is of course something that is very expensive for someone who is used to static analysis like me, but actually it's something that people in security do very often on smaller pieces of programs that are very challenging to prove. So what is the principle of symbolic execution is you are essentially going to keep very precise information attached to each pass, which is going to include the conditions before triggering the pass, and also precise relation between final and initial states of the pass. Okay? And of course, this is not going to work well if you have loops, because you cannot do symbolic execution. So in fact, in this case, you can go back to solution 1, beyond the bound you have state, which is only sound with respect to execution below that bound, so it doesn't sound with respect to all executions. And you have actually more ways to, that I did not include here, to actually run pass symbolically and actually do a clever join of the outputs, and to go back to some abstract domain like the Boolean phrase that I mentioned on the previous slide. And we had a very bright student, Tamara and myself, implemented this all and could prove some pretty challenging function using some abstract interpreter for Semantic. How much time? Very good. So I can talk about a very, so yeah, okay, so to conclude on this one, the main limitation of the static analysis we have seen here is cost, because essentially here we just use a reduction of to safety, which is a costly way, that is, we do a self-composition of the program, everything gets duplicated, so eventually it gets very costly. Now let's talk about something fairly different, which is relational analysis for hyperliveness. So let's go back to this smoothness example, and I will just fix one smoothness property, which is continuity. So essentially what continuity says is whenever you have, so we can first take a definition of continuity for functions from Rn to R. So when the function is continuous, it means that essentially it's, the function is continuous with respect to a set of variables I, so a subset of range 1n, if whenever you take a family of, I think I missed part of my definition. So, okay, I am sorry, I dropped part of my definition here, finished my slides a bit late, I'm sorry. So, essentially what it means is that if you fix variables that are not in I, the function that considers only the other variables is continuous in the straight continuity sense, exactly the same definition as I gave before. So if we want to see a few examples where this works, like polynomial function definitions work, are continuous, and if we have, so I will give more examples later. Here is more interesting example. Here you have a function with a test on x. So this test will introduce a discontinuity. That is, whenever you change at the point where x is equal to 0, you switch from this branch to that branch, you lose continuity. So this function this program will not define a function where u is continuous with respect to x. However, it's continuous with respect to yz. That is, if I fix one x, then whatever I read into the final value of u is actually a continuous function of y and z. Okay? So here is one more example. So this is actually cyclic favor function. So this function is equal to 1. So this takes 2 inputs. So this is from R2 to R. So whenever any of the 2 inputs is negative, you return 1. And otherwise, if you take, let's say for instance, y is between 0 and x, then you return 1 minus y divided by x. Okay? So, of course, this will mean that when x is equal to y, you are on the 0 element here. So this function is almost everywhere continuous. There is one discontinuity, which is the point at 0, 0. So that's one example of non-continuity. It's going to be a bit useful in 1 minute. So why is it useful? Well, it shows that things that we would like to do in static analysis, like maybe proving that the function is continuous with respect to I, and it's continuous with respect to j. So I would like to do one is continuous with respect to I union j, and that's not going to work. Because in this case, this function is continuous with respect to x, is continuous with respect to y, but it's not continuous with respect to xy because of this 0, 0 is continuous. So that's one example of one issue that we are going to have if we want to resolve over that problem. Another thing we would like to do, if we know that programs typically are compositions of operations, we typically have segments that in the semantic point of view correspond to function composition, we would like to also use mathematical theorems to resolve over composition. So there is one theorem which is called chain rule. Again, we are back to the calculus class. So if we are in dimension 1, it's very easy, very nice. It says if f is continuous, g is continuous, then if image of, f of A is included into whatever open where g is continuous, then f composed with j is also continuous. Right. If we want to extend this to functions over n dimensions, well, essentially this does not work so well anymore because we have to have continuity with respect to all variables. There is no way we just say we prove continuity with respect to a subset of variables in between. And we are going to compose this nicely. It's not going to work. So again, that's another issue that makes reasoning over this property pretty difficult. So what have we done? So I will, because I think I'm now going to run out of time in a couple of minutes, we essentially change the semantics and make it into a semantics that takes a pre-continuation as an argument. So essentially what our semantics does is computing something equivalent to collecting denotational style semantics, function from input states to output states, except that we take a pre-continuation and we just compute another transformation which includes the execution of the program. Okay? So, and we start essentially with whenever your program starts, we just start with the identity pre-continuation. So what we are going to do in the abstract interpretation is over-approximate using some abstract domain this identity pre-continuation. And whenever we are going to analyze one program step, we are going to have an abstract version of this semantics that is going to take an abstract pre-continuation into an abstract pre-continuation composed with your program. What abstract domain are we using? Well, essentially, we are going to use an optimized version of this abstract domain, which is essentially functions from sets of variables to sets of variables, and which is going to say for each set of variables with respect to which set are we continuous. Okay? So actually, there is a very non-trivial optimization which allows us to save a lot of memory and to go from this to x to p of x. I cannot give intuition in a few minutes, so I just refer to the paper for that. One last bit is that very often, if we want to resolve over continuity, we have to look into value information. So, and if we abstract only the relations using this abstraction, we have no information about the values at all. So we need to combine such an abstraction. So how are we going to do it? Well, essentially we make another abstraction, which is also an abstraction for relations, and which is going to abstract the post state of the relations, and we are going to do reduced product of this and the previous abstraction. And what this lets us do is just take a program like this one. So if this is computing sine function, if you can prove that x is in some range, because in some context you call this function, x is always positive, then this function will be continuous. Okay? So actually it's a reduced product of two abstractions. Okay, so I had one to conclude, but I think I will conclude. So thanks a lot.